Hello guys, so today we are going to introduce the second method of heat exchanger analysis called effectiveness NTU method. Now with the LMTD method, the task was to select a particular heat exchanger which met the prescribed heat transfer requirements. So a generic procedure was, first we will select the type of heat exchanger, whether it is a parallel flow or a counter flow or a cross flow arrangement. Then from the given data, by using an energy balance, we will try to find out all the temperatures, all the inlet temperatures as well as the outlet temperatures. Now with the temperatures, we will calculate the log mean temperature difference LMTD and correction factor if it was a cross flow or a shell and tube heat exchanger. Then we will either calculate the overall heat transfer coefficient U, or we will select it corresponding to a particular value from the data book. From all this data, by equating the heat transfer rate with UA LMTD, we will calculate the heat transfer surface area AS. Okay. Now the task is completed when we select the heat exchanger of the required area that we found. Now the LMTD method is best suitable for determining the size of a heat exchanger which is required to realize a prescribed outlet temperature. That is, we already know what is the temperatures at the outlet for a given mass flow rate and inlet outlet temperatures of hot and cold fluid. But usually a second kind of problem arises in heat exchanger analysis, and in this particular problem, we will be asked to determine the heat transfer rate as well as the outlet temperatures of the hot and cold fluid. The mass flow rates will be given and the inlet temperatures will be given. Additional to this, we might have already selected a type as well as size of heat exchanger. So here we will have the heat transfer surface area A. We will know this, but the outlet temperatures are not at all known. So now we need to evaluate whether the selected heat exchanger can perform efficiently or whether it can reach the desired temperature levels. So this required introduction of a parameter which is independent of temperature in order to estimate the performance of the heat exchanger. That led to the rise of our effectiveness NTU method. So for this, we defined a non-dimensional number called as effectiveness, which is nothing but the actual heat transfer rate to the maximum possible heat transfer rate. The actual heat transfer rate we already discussed in LMTD energy balance as Cc Tc out minus Tc in, or Ch Th in minus Th out. Here the Cc and Ch are the heat capacity ratios, which is nothing but the product of mass flow rate and specific heat. Now we also need the maximum possible heat transfer rate. So in order to estimate the maximum possible heat transfer rate, there can be a maximum temperature drop within the heat exchanger as Th in minus Tc in. That is, we have a hot water entering at temperature Th in. It has to be cooled by a cold water entering at temperature Tc in. Now the maximum reduction in temperature possible is what? The inlet hot fluid will be decreased to a temperature corresponding to outlet or the inlet cold fluid. So for example, the water is coming at 100 degrees centigrade hot water and we are passing a cold water at 30 degrees centigrade. The possible scenario is either we reduce the heat transfer rate either we reduce the temperature of the hot water from 100 degrees centigrade to 30 degrees centigrade, or we can heat the cold water from 30 degrees centigrade to 100 degrees centigrade. So these are the two possibilities. But the only way both can simultaneously happen is if the heat capacity rates Cc and Ch are same. So in order for this to be equal to outlet temperature, the difference of inlet temperature to be equal to outlet temperature, Cc and Ch should be same. but that is not the case in most criteria. So it will be limited by the fluid with minimum heat capacity. Hence, to find the heat transfer rate or the maximum heat transfer rate possible, it is given by C minimum into TH in minus TC in. Now the C minimum can be CH or CC, whichever is the smaller value. So if we substitute that in the equation, we will have effectiveness as either CH into TH1 minus TH2 by C min into TH1 minus TC1, or TCC into TC2 minus TC1 by C minimum into TH1 minus TC1. Okay. Now the advantage of finding the effectiveness is that once we know the effectiveness, we can estimate the heat transfer rate Q by multiplying the effectiveness with C minimum into TH1 minus TC1. So this is found from this equation where Q max is nothing but C min by TH1 minus TC in. Now don't get confused. In some equations we are representing as TH1 and TC1, while in others we are saying TC in and TC out. So basically one represents inlet and two represents outlet. Okay. Now the problem here is this effectiveness is represented in terms of temperatures, and in these temperatures two temperatures are not known, which is the hot water outlet temperature as well as the cold water outlet temperatures. So we need to modify the effectiveness equation in such a way that it is independent of temperature. Now this we have to do for both parallel flow as well as counter flow heat exchangers. So first we will discuss parallel flow. Now the derivation follows, the first half of the derivation follows the same procedure for our LMTD method, but we will discuss that here. So here the figure shows a parallel flow heat exchanger. Okay. So these are the same criteria. So we are taking a small elemental area, there is some temperature drop, so we are going to discuss the heat transfer in the direction of fluid flow. So we have dq is equal to u into dA into Th minus Tc. So here the hot water, if you check, the hot water temperature is decreasing. So if we take in the direction of heat transfer, final minus initial will be Th2 minus Th1, which will always give you a negative value, whereas Tc2 minus Tc1 will be a positive value. So to counteract for the negative value in the temperature, we are adding a negative sign here. This we already discussed in LMTD derivation. So this dq can be written as minus Ch into dTh, which is same as Cc into dTc. We are going to find equation for dTh and dTc. Subtracting these two, will get dTh minus dTc as minus dq into 1 by Ch plus 1 by Cc. Now we will substitute the value of dq as u into dA into Th minus Tc. We will take this Th minus Tc and we will integrate it. Alright. So here we will have an equation of this sort. From the brackets we are going to take out Ch. In order to cancel out this logarithmic ln, we take exponent. Okay, from this exponential equation we will have a base equation. Alright. Now we have already discussed the effectiveness equation as this equation in the previous slides. Okay, what is the problem here? Now here we have two unknown temperatures, Ts2 and Tc2. So we need to make this equation independent of temperatures, and we have to involve effectiveness into the equation. So from this effectiveness definition, we are going to rewrite it in such a way that we have an equation for Ts2 as well as Tc2 in terms of all the known values. So these two equations we are going to now substitute in the above equation. So that will yield, so we are going to eliminate Th1, Th2 and Tc2. We are going to substitute it. We are going to solve this equation, expand. We are going to take all the terms with effectiveness common to one side, and finally when we write effectiveness, we will get an equation of this sort. Okay, there is some Ch value, there is some Cc value, so you will end up with a derivation of this sort. So you can do that, and if any doubts come, you can obviously ask in the comment section. Alright, so here you can see Ch and Cc values. Okay, so there can be two cases. When Cc is greater than Ch, so what will happen? Cc will be the Cmax value and Ch will be the C minimum value. So that is being substituted in the previous equation. The equation turns out to be like this. Now there can be a second criteria where CH is greater than CC, then Cmin will be CC and Cmax will be CH. So you will end up with an equation like this. If we modify this equation slightly, where we take out Cmax or we try to make it similar to this one, we will find that these both equations are similar. So by rearranging, we will get a common equation of this form. So here you can see some peculiarities. There is a term UA by C minimum, and then there is a term C min by C max. Now this term UA by C minimum is a non-dimensional number called net transfer unit, or NTU, which is sometimes also represented as N. This NTU is a measure of effectiveness of the heat exchanger. The other non-dimensional number is Cmin by Cmax, which is called the capacity ratio, R, or sometimes also represented as C. So substituting these two values into the effectiveness equation, we now end up with an equation effectiveness equal to 1 minus exponential minus NTU into 1 plus R by 1 plus R. Now in some data books you can see it as mentioned as NTU, and in some data books you can mention it as C. So your academic questions may ask you to derive this effectiveness either in terms of NC or NTU, you can do it accordingly. So this is the effectiveness equation for a parallel flow heat exchanger. Now if you notice, this entire term is independent of the temperature. So now you can use this effectiveness to find out the heat transfer rate Q, and from the estimated heat transfer rate Q, you can now estimate what will be the outlet temperature of hot water as well as cold water. So that is how effectiveness helps in heat exchanger analysis. So similarly, we can derive effectiveness for a counterflow arrangement also. So here the difference is hot water, the temperature decreases in the direction of flow, but when we consider the cold water, the temperature here also decreases. So the negative sign arises in both hot water temperature profile as well as cold water temperature profile. So that will be reflected throughout the derivation. All the procedures are same. We will find dTh minus dTc. We will substitute for dQ. Once we substitute, we will integrate it upon 1 to 2 or inlet to outlet. We will get a logarithmic equation. From here we will take Cc common. We will modify this equation slightly, so they have took a minus out. So they have rearranged this equation also, Th1 minus Tc, so they will take a minus out. So once we solve that, we will integrate it. You will end up with an exponential equation while taking exponentials. All right. So we will get effectiveness now. So now we have an exponential equation. We have Th2, Tc2, which we need to change. We will substitute for Th2 and Tc2 in terms of effectiveness. So we will solve on solving and on reduction, taking all the terms common, effectiveness terms common on one side. You will finally end up with an equation of this sorts. Okay, so both these equations are almost same. And now if you substitute for UA by C minimum as NTU and C min by C max as R, you will have a effectiveness for the counterflow heat exchanger as 1 minus exponential minus NTU into 1 minus R by 1 minus R exponential minus NTU into 1 minus R. Alright, so once again, if there is any doubts coming in the derivation, please feel to comment in the comment section and I will get back to you. Alright, so now we have effectiveness for parallel flow and counterflow. Likewise, we can derive effectiveness for different cases like shell and tube, cross-flow heat exchangers. Like that we can do. Adding to this, there are some special cases where the values of R in this equation will be different. So when R is 0, we have to take the effectiveness as 1 minus e raised to minus NTU. When R is 1, for parallel flow we will have this equation, and for counter flow we will have this equation. Okay, now you might be wondering how we will learn all these equations. There is no need to learn by heart all these equations. These values are provided in your data book, so you can check in the data book under heat exchangers. All these equations are provided. So the description is given here, which is a counter flow counterflow with C equal to 1. Now mine here C is nothing but C min by C max. So all the definitions are given here. Sometimes there might be small printing mistakes. So this is nothing but C minimum, and here you can see C is represented as G minimum. Now here it is M dot, this dot is missing. So like that, small corrections you can make, but overall you will get the descriptions of the different types of cases and the respective effectiveness value. So by reading the question, we have to first identify what sort of heat exchanger it is, apply the necessary relations to get the effectiveness. Once we get the effectiveness, we can find the heat transfer rate Q based on the inlet temperature conditions given in the question. Once we get the heat transfer rate Q, we can now estimate the outlet temperatures. So this effectiveness NTU method is mostly used when you only know the inlet temperatures and you do not know the outlet temperatures at all. Another important condition is the area of the heat exchanger will also be specified in the problem. Okay, don't worry, we will be covering some basic problems in the coming lecture. Hope you understood this lecture. For any doubts, comment in the comment section. So see you in the next lecture.